personal pleasure to introduce Oliver Junge, and he will talk about entropic transfer operators.
Yeah, Catherine, thanks. And also thanks to the organizers here for having me for this extended period. So my first time in Cambridge, and I already got quite a few good impressions on how to design, properly design math buildings. So we have a math building in Munich, which is not designed properly. So no, it's not. It's, well, yeah, but here, well, anyway, okay. So, yeah, so this is a joint paper with two colleagues here, Bernhard Schmitzer in Tübingen and Daniel Mattes in Munich, which is essentially about discretizing transfer operators. Right, and so another way to phrase the goal of this paper here is given a deterministic map, so simply a map on a, say, compact metric space, how do you derive a model, a finite model, which you can implement on a computer, that captures the important features of the map? Well, evidently, what important is dependent on the application, on the context. In this case, the goal is to capture macroscopic features. You know, well, I'm going to give you examples on what we mean by this in a second. Yeah, so that's the goal, and the double arrow here simply means, well, this map doesn't have to be deterministic. It can be multi-valued, or it can be a transition function, yeah, like a Markov chain. Think of a Markov chain. So Fn is typically a Markov chain simply. All right, now, how do we do that? Well, the idea is to, instead of looking at the map, we look at the transfer operator, F sharp, which, well, depending on the context, is a map on bounded measures, or rather on densities, or on well, L2 functions in general. That's the setting that we're going to go to later. So that's a linear map, and that's the important thing, of course. That's a linear map, and that's why Koopmanism is so successful, yeah, because, I mean, linear is easy. So it's a linear map, but of course on it's an operator on an infinite dimensional space. Yeah, so again, either on the space of measures or on densities, but in any case, it's an infinite dimensional space. So it's not that easy. It's actually not easy, because dependent on which space you you consider this operator, the spectrum might be different. The spectrum might be complicated in the sense that you not only have a point spectrum. And so all sorts of questions arise that from both a theoretical point of view and also from a numerical point of view are actually not that easy. Okay, anyway, let's assume we can approximate this linear operator by a Markov matrix, so like a stochastic matrix, reliably in some sense. Then and then the hope is that, or the goal is that that the important eigenvalues, and by important I mean the large ones, the ones close to the unit circle, that from those eigenvalues and the associated eigenvectors, we can construct a coarse model that I was alluding to on the on the previous slide. Yeah. So again, the coarse model will be a Markov chain, a weighted directed graph, where the weights indicate transition probabilities. And here's one example how this might look like. And then this is the coarse model I'm looking for. Yeah, so that's the goal. Okay, well, a few basics on transfer operators. I mean, I know this is probably completely redundant, but let's go through it anyway. So what's the transfer operator? Well, let's say, okay, so we're given some probability measure on state space. And let's assume that you have a bunch of points distributed according to that measure. Yeah, so the probability to find one of those points in a given set is mu of this set. Then what's the probability? So now I map those points by the given map f. Yeah, I look at the image points fxj, and the question is, what's the probability measure that describes the distribution of those points? Well, that's easy to derive. Yeah, I'm looking at the probability that some image point is in some measure. Well, if the image point is in some set, if the image point, if the image of some point is in some set A, well, then the point must be in the pre-image of A, and then I'm simply using the definition. Not the definition, I'm using that I know how the points xj are distributed, namely according to mu. So the distribution of the image points is given by the mu measure of the pre-image of some set. So formally, I get a map which maps some measure to, well, to this measure here, to the push-forward measure, as one says. And as a map on measures, this is a linear map, as I already mentioned. Okay, so that's the transfer operator. Simple example, how do you deal with that in practice? Well, there are formulas that one can derive. For example, if you look at measures which are absolutely continuous with respect to, so let's say, Lebesgue measure, then you can actually derive an explicit formula for how this operator acts. But here's an even simpler example, namely if we have a linear combination of point measures, well, then by this very simple derivation here, you can see that the push forward of this measure is simply given by the same linear combination of the point measures at the image points. So for point measures or linear combinations, it's trivial to compute the push forward measure. And this is so simple and numerically so easy that it's very tempting to try to exploit that numerically. Yeah, but on the other hand, problem is, of course, that this measure here, I mean, you're in completely different measure spaces, right? So the first measure is a linear combination of, I mean, it's supported on the original point cloud, and the push forward measure is supported on the image point cloud. So not directly comparable. So what do? Well, the idea was to somehow map from the image space, so the measures supported on the image points, back to the measures supported on the original point cloud. And well, that and we particular in this work here, we did that using optimal transport. But anyway, I'm getting ahead of myself. Okay, so first observation, the transfer operator is a Markov operator, so it preserves a non-negativity and preserves measures. So it's Markov, and as I already alluded to, it induces a corresponding linear map on densities, which is which, for example, you can define by this duality shown here. Yeah, and people in the field here, of course, immediately recognize that this is that here the dual of the operator appears. So this is typically called the Koopman operator, composition operator. Right. Yeah. So F sharp induces a linear map on densities, well, if the measure that we're given here, if mu measure mu that we are given is invariant, then this is actually a self map. But in general, of course, later mu will be the point measure given by the initial point cloud, and so it's typically not invariant, of course. All right, now, yeah, okay. A few words on invariant measures. So an invariant measure is a fixed point of the transfer operator. An ergodic measure is an invariant measure such that any invariant set has either zero or full measure. And the nice thing is that any invariant measure is a convex combination of ergodic measures. Now, why are invariant measures interesting? Well, here are two classical theorems. So the Poincaré recurrence theorem, if I have an invariant measure, or if mu is an invariant measure, then for any set in state space, the subset of those points that return infinitely often to the set, which is denoted by A naught here, has full mu measure. Yeah, so mu, an invariant measure, is characterizing recurrence. And then the classical ergodic theorem here by Birkhoff, if I have an ergodic measure, well, then the temporal average of some observable, L1 observable in this case, on the left-hand side, so this is the temporal observable, I'm averaging the value of this observable h along the trajectory is equal to the spatial average of this observable with respect to this invariant measure mu. Right, okay. So an invariant measure is an eigenmeasure at the eigenvalue 1 of the transfer operator. And you might ask, what about other eigenvalues, if there are some? Well, if you have some roots of unity as eigenvalues of the transfer operator, then it turns out that this characterizes macroscopic cyclic behavior. So you can decompose the state space into a sequence of sets which are cyclically permuted by the map. And if you have an eigenmeasure at a real eigenvalue, think of, starting with, think of lambda being close to 1, then you can actually decompose the state space into two sets, A plus, A minus, which are simply which are characterized by the nodal structure of the eigenfunction. I'm assuming here that the eigenfunction is absolutely continuous with respect to some invariant measure. So these are the nodal, so A plus and A minus are the nodal domains of the associated density. And and then you have this nice relation between the like self like the invariance ratio with respect to this measure nu here. So this is the nu. That's the probability with respect to nu that that you map into the set A. And then the statement here is that if you have that eigenvalue and the associated eigenmeasure, then you can decompose the state space into these two sets, A plus and A minus, which, if lambda is close to 1, have a large self-invariance ratio. We, back then, a couple of years ago, we called this almost invariant. In other contexts, this is called metastability. So these two sets, A plus and A minus, are metastable. And yeah, and these are two examples of macroscopic structures. Yeah, so you have cyclic behavior, you have metastable behavior, or you might also have almost cyclic behavior if you have an eigenvalue or eigenvalues which are almost roots of unity, which are close to roots of unity. Then you don't have an exact cyclic behavior, but you only map into the next set in your sequence with a certain probability. And yeah, and the nice thing is that given some eigenvalue and the associated eigenfunction, you get this decomposition into either the cyclic structure or the metastable structures automatically by looking at the associated eigenfunctions or measures. Yeah, so that is how you derive this coarse model that I alluded to in the beginning. Okay, well, here's a famous method for constructing a Markov matrix approximating the transfer operator, Ulam's method, which essentially says, well, let's decompose the state space into a couple of sets. These are the sets A, J here. And then let's simply look at how probable it is to map from one of those sets into another one. Yeah, so these are these transition probabilities P, J, K here, giving me a large matrix, transition matrix between the cells of this covering. Yeah, and this is a Markov matrix, and I can view this as an approximation to my transfer operator. Now, how good is that approximation? Well, that is not exactly easy to answer. There are results for certain classes of maps by many authors where you can get exact statements about how the eigenvalues of this matrix relate to the eigenvalues of the original transfer operator, whether you have convergence if you let the number of sets go to infinity, and so on. All right. But okay, so what's the? I mean, this method has been quite popular, like 20 years ago. But the main problem is, of course, that if you consider a map on a high-dimensional phase space, then it's not quite evident how to choose this disjoint covering with these sets AJ. In particular, if you do this naively and you have if you have a high-dimensional state space, then you will require a huge number of those sets, and the problem will become computationally very expensive, if not unfeasible. So people have been looking for other ways of approximating the transfer operator, and well, in the end, it turns out that Ulam's method is essentially simply a Galerkin approximation of the transfer operator using a dictionary, I'm using the Koopman speak now, of characteristic functions supported on the sets AJ. But that's not the only dictionary that one can think of course. Yeah? So if I talk about a Galerkin approximation, well, I can think of all sorts of dictionaries that I can use for this approximation, and well, another dictionary leads to another method here, leads to another approximating matrix with different properties then, of course. And yeah. All right, well, as I already started to mention, the idea here in this paper is to say, well, I know for a given point cloud, I know what the image of some measure is. I simply, I mean, that was the example with this point cloud that I gave for the transfer operator. So for a point, in order to compute the image of a point measure is trivial. Can I exploit that? Yes, if I'm able to, so to speak, pull back measures from the space of measures supported on the image point cloud back into the space of measures supported on the original point cloud, and we're going to do this using optimal transport. So how does this work? Let me give you a few words on the history of optimal transport. It's actually a pretty old problem. So we're given two probability measures, or think of piles of sand. Yeah, so sometimes some distance that will appear later here in this context is also called the Earth mover distance, which is kind of a nice mental image, because what you're actually trying to do is you're trying to transport the measure mu to the measure nu, and you would like to minimize your work. Yeah, you would like to do as few earth-moving operations as possible. So in addition to these two measures, you're given a cost function which tells you how costly is it to transfer mass from one point x to another point y. And now the goal is, again, as I said, to move the measure mu to the measure nu. And at the same time, we would like to minimize this cost function here. Now, the original problem, already phrased by Munich in 1781, was find a map which does this. So find a map phi, a deterministic map, such that the push forward of mu under phi is nu. That's the goal, and such that this cost function here is minimized. This integral of c over mu is minimized. Well, unfortunately, it's very easy to find an example where such a map cannot exist. Yeah? For example, if mu is a point measure on a single point and nu is supported on 2 points, well, then evidently there's no deterministic map which solves this problem. So how do you deal with this? Well, the idea that turned out to be the proper one, or one proper one, is due to Kantorowicz, who proposed not to use a deterministic map, but to instead consider a transport plan, or you might also think of a stochastic map, actually. So the transport plan is a probability measure on the product such that its marginals are the given two measures, mu and nu. Yeah, so gamma of A and B is then the amount of mass transported from set A to set B. And the cost function that we now need to minimize is simply the integral of the cost function with respect to the transport plan that we need to find. Yeah, so that's the goal then, minimize this functional here. And a minimizer exists, for example, if the cost function is continuous. And well, if the cost function is the typical one, namely simply the Euclidean distance, then it turns out that that a minimizer is almost a map. It has sparse support. But this cost function, or this function, is actually not quite nice to deal with because it's convex, but it's not strictly convex, so there's no unique minimizer. And so the question was, how do you deal with that? Well, one popular method is to regularize the problem a little bit by adding the entropy of the transport plan with some small epsilon here. And then if you do that, well, and it turns out then the problem really has a unique minimizer, which is of a very nice and simple form, namely the optimal transport plan is absolutely continuous with respect to the product measure of the given two measures. And the density is simply a Gaussian with, well, the given cost function and these two potentials here, alpha and beta, which are in there because we need to realize the marginal constraints, namely we need to make sure that the two marginals of gamma are mu and nu. So that's what we would like to solve in the Excuse me? Yes, yes, exactly. Yeah, so the alpha and beta are uniquely determined by the marginal constraints. Yeah. Right. So that's a nice problem then. Yeah. And if you look at a discrete version of that, yeah. So now let's suppose that the two given measures are finitely describable, so to speak. So are given by either point measures. I mean that's the particular setting we're going to use later. Yeah, so think of point measures now. Then, well, the marginal constraints simply say that either the row sums or the column sums of the transport plan, which is now simply a matrix, of course, are the mu's and the nu's, respectively. And the discrete optimization problem looks like this. Yeah, we need to minimize, we need to find a matrix gamma such that this functional here, this functional C, is minimal. And again, the unique minimizer is of a very simple type, of course, which looks exactly how I just described it, just that it's phrased in terms of this finitely with finitely many parameters. Yeah. No, but there's an algorithm to compute them. No, there's no explicit expression as far as I know, but there's a very nice simple algorithm which back in 2013 by Couturi, which back in 2013 made quite a bit of buzz because it finally made possible to solve problems, to solve optimal transport problems of this type quite quickly. Right. Okay, so, well, so this is a little bit of background on optimal control theory, but how do we use that now?
Sorry, I didn't understand this argument because, so you compute iterator the alpha, beta, and C. What about C?
Okay, so we initialize, so C is given, that's the given cost function.
Oh, that is your cost function.
That's
So this will be something like squared.
Yes. Think of Euclidean distance squared. That's the typical case. Yes. Exactly.
Of the points.
Yeah. So think of a point cloud, x1 to xn, and then you compute the pairwise distances between all points, and that's your matrix Cij. Okay, now how do we use that for discretizing transfer operators? Well, the first observation is that a transport plan, so a probability measure on the product space, x cross x, it uses a linear map like this. Yeah, so I'm defining G, or the image of some function h under G by evaluating this integral here for all continuous test functions. We actually don't need this very general form. We can specialize to the case where the transport plan is absolutely continuous with respect to this product measure. And in this case, this induced map G is simply this integral kernel map. So that's nice. And now, so this is like the core idea now to how we get a map which is a self map. How to get well, it's not an approximation yet. It's at this point it's only like a smoothing or regularization. But the crucial point is that initially my transfer operator is not a self map. Yeah, so it's mapping from the space of densities on the point cloud that I'm given to the space of densities of the image point cloud. So it's not a self map. Now, by composing T with the map induced by optimal transport from the image point cloud measures back to the measures on the original point cloud, I do get a self map. Yeah, so that is the crucial point here. And well, the explicit form turns out to be quite familiar. Yeah, so we simply get an integral operator where with a particular type of kernel here, which is given by the solution of the optimal transport problem from the image, from the measures supported on the image point cloud back to the measures on the original point cloud. Yeah, so I mean, in principle, we could have written. I mean, the particular form of this regularized operator here is pretty standard. Yeah, you might as well use Gaussians for G epsilon. The only difference is actually that in addition to having a Gaussian, yeah, with the distance of f of x and y in there, we additionally have these two potentials alpha and beta, which realize the marginal constraint, which in the end ensure that this operator T epsilon here actually preserves the invariant measure.
How do you choose the epsilon? Is that matters or?
The epsilon?
Yeah, is that matter?
Well, by experiment. Yeah, I mean that's a free parameter. That is kind of well, I'm going to show one simple example of a simple circle rotation where you actually get where you need to make sure that the epsilon is balanced between like in between the number of points that you have. The more points you have, the smaller you can choose epsilon, and the like the size of the features that you would like to approximate. Yeah, like the frequency of the eigenfunctions that you approximate. Yeah, so if you aim for to approximate eigenfunctions with high frequency, then evidently you cannot afford to have a large epsilon. So there are some hints on how to choose epsilon, but in the end, it's typically chosen experimentally. And a good idea is to actually look at the spectrum of this T epsilon here, or rather the discretized version of that, independence of epsilon, and then to only consider those eigenvalues which show some persistence in epsilon. I'm going to show that in the examples later. Yeah.
Is your T.
So I was wondering, so the fact that it's a Gaussian, does it depend on the fact that it was the entropy?
Yes, exactly. So that is a direct result of the fact that I'm using the entropy. Yes, yes. Yeah. I would get a different kernel if I used another regularization.
Then would it still be a weak solution?
That I don't know. I don't know. I assume so. If the regularization has similar properties in terms of the functional, then probably yes. But I don't know. That's.
Is your T epsilon doubly stochastic with respect to mu?
Yes. Yeah, it preserves mu. Yes.
So let's say you just made with Gaussian, with standard Gaussians, the asymmetric frequent operating estimate, and then you applied some to the doubly stochasticized, then you get something very different.
I don't know, but maybe not. Yeah.
I'm sorry, I'm a bit confused. If I know T, why do I care about T epsilon? Or do I not?
Well, T is not a self-map. So I cannot compute eigenvalues because it's not a self-map.
Oh, I see.
So what you're saying is like if you discretize that integral with finite number of data, then you should be able to analyze how epsilon is depending on the size of the data. Maybe that analysis exists.
Well, there's no like hard analysis, but in the case of the circle map that I'm going to show in a second, that there's there are estimates the estimate on the error of the eigenvalues indicates how to choose epsilon.
But before even eigenvalue, usually you take the norm between operator first, right? Then eigenvalue proceed.
To choose the epsilon.
Yeah.
So I don't understand. Mu is the invariant measure.
No, mu is not necessary.
Imagine that is the invariant measure. Then I would expect it to be a delta function, but G epsilon is not a delta function, so I'm a bit confused.
Okay, so assume mu is invariant, then T is already in a self-map. I wouldn't need G epsilon.
Yeah, but this is a completely general formula, right?
Yes.
So imagine that I don't know that is the invariant measure. I have some measure, it just happened to be invariant,
Okay.
but I'm not aware of that. Then I apply this formula, it doesn't seem to work. Maybe I'm something that I don't understand. Well, because I would expect it to be G epsilon, I would expect to be a delta function, but that would be a delta function.
But
all
then
around.
the
G epsilon is not a G epsilon is a smooth version of the identity. Then it's like a blurring of the identity. I mean, G epsilon is this integral kernel.
Yeah, this integral kernel, you would like to have H to go to H, right? That's what you would like.
Yeah, but you don't have that. G is this.
I understand that G is there, but what worries me is that it seems that the invariant measure is not a fixed point of this operation.
Now I understand the question. Yeah, sure.
Epsilon going to 0 to C. So I don't know, even for the invariant measure, it doesn't give you immediate, I mean, maybe it's perfectly okay, but I wanted to understand if this is the case.
So you can like here some.
So like a random H will not map
Als G
back to
epsilon
itself.
affinity and
Yeah, yeah, sure.
Yeah, I understand.
One
but,
function.
no longer
yeah,
the
I understand. If you take the invariant measure,
Yeah, but the invariant measure is modeled if you take like H being the one function.
that's correct.
So when that is mapped to itself, it's still
Okay,
a
so
self
one could still,
and you're smoothing the one function, which doesn't really do anything.
I see. So sorry, I had the wrong intuition. Okay. You just approximate one, not the delta function. Okay, fine. Then it would work. Yeah, okay, so.
No problem. All right, here's a picture. Yeah, so, well, it's what I just described. Yeah, so you have this deterministic map F, and then you have this stochastic transport plan which maps back to mu. Okay, that's the same slide. Sorry if it's a little bit crowded. It's the same slide, except that now my measures are finite. Yeah, point measures, finite point measures. And then I do the same thing again. And what I get here is a finite representation of the entropic transfer operator, and the operator is represented by this matrix here, where I evaluate the kernel, which is the density of the optimal transport map at, well, some point, and the image points. Yeah, so I take all the pairwise combinations of points and image points. So that is what I'm computing in the end. Yeah, so I mean that is the matrix that results from this discretization, and that's the matrix I'm going to compute eigenvalues and eigenvectors of.
Is that a bistochastic?
That is a bistochastic matrix. Yes, exactly. Yeah. By construction, because G yields a bistochastic matrix. That's how these potentials alpha and beta are computed. Okay. Well, in order to derive a convergence statement, I need to map, or we need to map back from the space of point measures into L2. And we again do this by optimal transport. Yeah, so this is, I mean, that's not, this is not important for the numerics. This is only important for the convergence statement, where I now, well, map from L2 of mu into the discrete space, then apply the matrix, so to speak, and then I map back into L2 of mu. And then I get an operator which I can compare with the original non-discretized but regularized transfer operator. And the statement is that if my point cloud or the point cloud measure converges weakly to mu, then this sequence of operators converges to the regularized transfer operator in the operator norm. And this fact then enables me to, okay, yeah, picture of this construction here. Yeah, so yeah, in addition to having the map and the optimal transport back to the mu n measure space, I'm additionally using these Pn constructions in order to get into L2 of mu again. Well, the fact that I now have this operator convergence enables me to use standard results on the approximation of eigenvalues and eigenfunctions of compact operators. T epsilon is a compact operator. Yeah, it's an integral operator. It's actually a Hilbert-Schmidt operator, so it's compact on L2. So yeah, I can simply use these standard results on approximating eigenvalues and eigenfunctions of compact operators. Right. Okay, here's the example that I promised. So simple circle rotation. Lebesgue measures invariant, of course. I can very easily write down the transfer operator. I can explicitly write down the eigenfunctions and eigenvalues. So the question is, how well do I approximate these? Well, since I'm not approximating the eigenfunctions of the unperturbed operator, but I'm always approximating the eigenfunctions and eigenvalues of the regularized operator T epsilon, I need to compare those two. So here are the eigenvalues of the discretized operator, and I'm comparing these to the eigenvalues of the regularized operator, yeah, which is given by which are these here approximately. So these are not the exact eigenvalues of the regularized operator, but very close. Yeah, and then there's this estimate here, and well, this is what I was mentioning here. So in order to get have this constant small here, you need to balance epsilon such that it it's kind of doesn't interfere with the discretization scale. Yeah, so n is my is characterizing how fine a discretization I have, and k is like the frequency, the maximal frequency that I would like to approximate. So the larger the frequency, of course, the harder it will be to approximate, and the smaller I would need to choose epsilon. So so I only get a good approximation to some eigenvalue if the frequency is not too large, and if I have a sufficiently fine discretization, of course. I mean, in some sense, that's.
Okay. Yeah, maybe I cannot follow everything, but it seems to me that this looks very much like what would happen if I would take the convolution with the Gaussian of size epsilon, more or less, of the dynamic. Take the dynamics and then I add a noise of size epsilon.
Yes.
And then once you convolve with the Gaussian, of course, there is a smoothing, so you can approximate even by Ulam and you can compute stuff.
Yes.
But I mean, is this any better? I mean, can you compare it?
Oh, I don't know. That's a good question. No, I don't know. Maybe not. I don't know. It is indeed. No, that's right. You might get similar estimates with plain Ulam. It's just that I didn't see those.
No, that it looks reasonable. That
I agree. Yes.
Because in the previous slide where you showed the approximation, it's just an approximation. Do you have also some estimate of the error, or it's just that? Yeah, no. The next one, there was the proposition 2, yes.
Yeah.
It just shows that you converge in.
Oh no, that is not that we don't have a quantitative statement there. No.
It's for positive epsilon. For fixed positive epsilon.
For fixed, oh yeah, sorry, yes, for fixed positive epsilon. Yeah, so we always only approximate the regularized operator for fixed epsilon. Yes. Right. Okay. Well. some experiments. So here's the experiment on for the circle map. So well, we've chosen a particular regularization parameter here, and then you get this spectrum. Well, exact is not quite true. Exact up to a very small error, exponentially small error here, and then the approximation is pretty good. Yeah, so it's I mean it's in the eyeball norm here, I admit, but
Sorry, what do you mean by exact is you take your spectrum, you multiply by e to whatever.
exactly. Yeah, so these are these numbers here, which are not the exact eigenvalues of the regulars, but up to very.
How do you get that exponential, fast convergence epsilon goes to 0? That term. Epsilon.
How do you get this one? Are you asking for the proof now?
I mean, intuition, it's that the proof must have some.
I don't have an intuition.
Okay.
That's from the derivation. I don't know.
Because what's killing you is
Okay. It essentially results from. No, it doesn't. No, I don't have an intuition. No.
Is the error primarily in the magnitude or balance?
No, it's the magnitude. It's
because the second part is easy to see, right? Because epsilon is killing you, right, on the denominator. So you need a lot of data, but you have that assumption, so it's okay, right? K equal to 0, you don't have that scale.
I guess the variance, right? You're trying to approximate variance. They're super.
Yes.
Is this using some out of box approximation result, or it's
No, that is. I mean, I wouldn't claim that there's a simpler way to derive this, but in the paper we do this from it's a computation. Yeah, it's a rather lengthy derivation. Yes.
I'm a bit confused because the eigenvalues or the lambda k's are all in the unit circle, and
Yes.
and then they should be multiplied by some exponential. They should all be smaller than.
Yes.
But on the pictures, it seems like there were some eigenvalues larger than 1.
No.
No.
Smaller.
Ah, okay. So maybe it's.
So blue, the light blue
okay.
is the unit circle, or unit disk. Right. So for this simple example, it seems to work quite well. Now here's a slightly more challenging example. So the classical Lorentz system, where we use an ergodic sampling for the point cloud. And here, and that is what I mentioned before here now we show the real spectrum, so only the real eigenvalues of the matrix independence of epsilon. And well, for very small epsilon, you get a lot of eigenvalues, which is to be expected, since for epsilon equal to 0, the matrix is actually a permutation matrix, right? And so the spectrum will be on the unit circle. Now, as we increase epsilon, a lot of eigenvalues at some point quickly drop to 0. But there are, in this case, there are 2 or maybe 3, it's a little hard to say here, but at least 2 which persistently stay at a reasonable scale close to 1 for quite large.
What is the difference between dotted line and solid line?
There's no difference. It's just that the solid line is dotted with dots very close to each other. Yeah. So how did we compute this? Well, we fixed epsilon, and for this fixed epsilon, we computed the spectrum, and then we plot the eigenvalues. So it's, I mean,
So on each vertical slice, you're plotting many eigenvalues.
yes, yeah. So for each vertical slice, that's one computation.
Yeah. So if you take the epsilon goes to say minus 10 to the minus 8, does this goes to the continuous spectrum?
Well, I mean, I don't know. It's
Not for fixed.
that's fixed and fixed,
Oh,
yeah,
fixed.
and fixed.
It's
So
very hard to realize, Prof.
yeah, you would exactly. You would need to somehow increase n, and that's not what we did. Yeah, so we have two. I mean, we compare two experiments with different values of n just to see how robust this picture is with respect to the number of points. It's reasonably robust, I would say. So in both cases, we have these two eigenvalues which persist over a reasonable.
So which two are you talking about? Sorry. You say two that persist. So which two am I supposed to?
So these two here.
Oh, that.
Yeah. So.
But what happens for the larger n? Do we have a double eigenvalue 1?
Well, we have a double eigenvalue 1 until this point, and starts to drop quickly. So these are typically isolated points in the point cloud, which have a larger distance than the rest, and they appear as like fixed points. Yeah. So this is probably, I said it's a wild guess now. This is probably a point close to the origin.
Okay.
Which is a fixed point, and then
Or close to one of the.
or maybe close to the other equilibria. Yeah.
So if I understand correctly, I mean, this system finally is a finite system, right? You have finite number of points.
Yes.
So that means that every orbit is periodic, pre-periodic, something like that, right? Because what can they do? I mean, the finite system, they're only periodic and pre-periodic orbit, essentially, right? So each one will support an invariant measure, so an eigenvalue.
Well, it's not necessarily a periodic trajectory that we use here. We take some random initial.
No, I understand. But once you discretize the system, then you have essentially a Markov chain on its own.
Oh yeah, sure, of course, yeah.
But it's a Markov chain. It's not a deterministic system anymore. That's what I wanted to understand.
No.
The discretized situation now is a Markov chain.
It's a Markov chain. It's a Markov chain, except if I did the computation for epsilon equal to 0, then the matrix would be a permutation matrix. Then it would actually be a.
Yes. And then you will have only periodic orbit.
Yes.
Yeah. Periodic orbit.
Yes.
So that means that when epsilon is very small, then this Markov chain starts to have a kernel that is very singular, right? Yeah. So that's why you could have, because I mean, on any periodic orbit, you would have an eigenvalue of 1, right? Because that would be an invariant measure. So you can maybe see more in degeneracy of the eigenvalue 1 when epsilon is very small.
Yes. Yeah. That's exactly what we have. So we have a lot of eigenvalues at 1 here that drop when we increase epsilon.
Yes. They should drop, but with some time.
Yes.
At a certain point, you see that they are not really eigenvalues.
Yes.
Okay. Makes sense.
What do you mean by equidistant sampling of long trajectory?
Oh, in time, equidistant in time. Yeah. So we have a flow. We have a flow map, and we don't change the time.
From the plots, is there a way for me to tell what's the optimal epsilon to choose in application?
Well, I wouldn't say optimal, but I mean any epsilon that is roughly speaking larger than 10 to the minus 1 is reasonable in some sense. I mean, admittedly, it's not clear how to deal with this eigenvalue, for example, or with this one. Yeah, so, but I mean, heuristically, I would say the two large ones that persist, one could be quite confident that those are interesting features.
Oh, I see.
That's how I would take this.
So certainly for small epsilon, the spectrum is very wide. It changes a lot from these pictures, right?
Yeah. So exactly. So it doesn't make sense to look at to put some interpretation onto eigenvalues of functions beyond 10 to the minus for epsilon smaller than 10 to the minus 1. Yeah, so that it's just probably those are probably eigenvalues that are related to the discretization as we just discussed, to periodic orbits that support variant measures and then are slightly perturbed.
If you do this in a purely data-driven way, like how machine learning people do it, like they will always find usually the best regularization parameter of some test set problem, and then they do cross-validation to find what is the best regularization.
So what's the objective function for if you say best?
Minimal, the smallest error in the test set. Your problem.
Okay. Well, I mean, this is purely data-driven. We have a point cloud and an image point cloud. That's it. Nothing else. We don't have a map. We don't have the explicit formula for the map. Just this is a purely data-driven.
But so then, if you need a computational method to choose epsilon, I'm curious if that method will tend to err on the side of small epsilon or large epsilon.
Well, I would rather recommend to look at this picture instead of choosing a fixed epsilon, trying to choose a fixed epsilon, because there is no ground truth here. Yeah? The only thing that you have are the data points. You cannot compare to a test data set, a validation. You don't have a validation data set. Yeah, so.
That question there.
Maybe related to that, so if you do for some subset of your data or something, and then you get similar, or for different, so maybe related to that proposition too, right? You have n, so corresponding to more and more data points. Is there some condition on how they are sampled? For instance, ergodic sampling or mesh or
no, the only thing that you need is a weak convergence. Yeah. Okay, and finally, I'm over. So last example is on a really large, from my perspective, large dimensional problem. So a molecule, classical test problem where the data is now given by the positions of the heady atoms and their images. So that's a problem in R30 now here, and yeah, so each point of my point cloud is a point in R30, and then I have their image points, and this is how the spectra look like. And here you see that even clearer, that probably there are two eigenvalues which are interesting here. Yeah, and well, if you're asking for an optimal epsilon, then I would say any epsilon between 5 times 10 to the minus 3 up to 2 times 10 to the minus 2 is good. So yeah, so that's yeah, and then from the corresponding eigenvectors to these two persistent eigenvalues here. Yeah, so these are the eigenvectors for various epsilon here. So you can it's pretty robust, evidently, again, with respect to epsilon. And then using, I'm sorry, CBA, not k-means, you can derive the corresponding features of the molecule, which are certain geometric shapes that in which the molecule is staying for quite a long time. So this is the interesting chemical information
for the chemists. All right.
I don't understand this molecule. Is it a classical model?
That's a very, very
Classical.
Okay, classical.
Yeah,
So
that's
it's calculating stuff. Okay.
Yeah, it's a very tons of papers on this one.
No, but I was wondering if the equation of motion are classical or quantum mechanical.
Oh, no, it's classical.
Okay,
Yeah,
fine, fine.
no, it's no quantum mechanics.
Yeah, so, all right, so that's it. Thanks very much.
Thank you, Oliver. There are a number of questions, I guess.
So say your mu in low dimensions like your Lorentz, so rotation. So you took mu to be the beta, and then you want the transfer operator with respect to the beta. Then can you get a good estimate for the invariant measure, the ACIM case where it exists?
Well, the approximation would still be on a point cloud, so you would get some linear combination of the point cloud measure.
This is something you know you can make a small random perturbation of your deterministic transfer operator. In the limiters, the perturbations go to 0. What you get, say, as the limiting invariant measure. For each perturbation level, you have something unique, typically. And then you get, this is like a selection principle to select something in the limit. And what you get in the limit is very sensitive to the type of perturbations that you do. Oolong is often very nice. This seems like a sensible selection principle. Do you know anything about what happens in the epsilon goes to 0 limit?
Not really. So, I mean, you know these results by colleagues here and colleagues who are not here on stochastic stability of these spectra and the eigenfunctions, and there are more recent results on stability of the entire spectrum for Morse-Smale flows, and I forgot the names of the authors, but
Saying like your G epsilons with what this is for.
oh, I didn't check that, but it looks reasonable. Yes, yeah.
If it's not an invariant measure, wouldn't the optimal transport map be like as epsilon goes to 0, you get the map? Like you've got two different measures, quite different measures, and so you'd have an optimal transport plan between them, and it was some map. So your dynamic is now not close to your original map because you added this extra thing.
Well, like usual, like you take the bait, you push it forward, you don't get the bait.
Yeah.
But that's how you define the things operation.
Yes, I guess then you're like trying to transform your push forward map, like your push forward of the bait back to the bait, right? So
I'm not sure whether I got the question.
I mean, this is what the push forward is. You take the bait, push it forward, you take the rate negative with respect to the bait, and that's your updated density.
yes.
So I think it's analogous to what all of this doing.
Yeah, that's yeah, exactly. That is what I'm doing. Yeah.
That's another question.
Yeah, for your molecular experiment or example, do the eigenvalues, the stability eigenvalues that you obtain correspond to the inverse of the timescale it takes for the molecule to get the different?
Yeah, good question. I didn't check that, but I hope so. Yeah, that would be a nice consistency check. Yeah,
Indeed. Yes.
So can I? So it seems like you get the leading spectrum of this operator. Let's say an approximation of regularized leading spectrum of this, right? One part of your talk in the beginning, you're saying like, I want to use this as a basis for reduced order modeling,
Mhm.
right? So my question would be like, okay, fine, now you have this, construct your model or your reduced model. How good is this model in predicting?
Yeah, valid question. Um, so we don't have any result in that direction. Well, there are a few results in the Koopman.
Which one would you
Literature.
guarantee that I should read? There's so many. It's like you go to
That's the hard-
SIAM dynamical systems. It's entire 4 days Koopman.
Yeah. I don't have one particular in mind. It's, I mean, yeah, it's a valid question. Yes.
Yeah, let's find out in the next couple of days, I guess. April? Yeah.
I just wanted to mention quickly because there was questions earlier about first the 1/8 epsilon thing is like specific to that circle map.
Yes.
And it's related to the frequency. That's why you have that k appearing, and it just is due to effectively it's an eigenvalue problem for that rotational frequency. So you can essentially like take out a certain section of this function around 0.
Okay.
And this, like how much of the function you take away, you're taking like a little epsilon square. So how much of the function you take away inside of that epsilon square is why you get this exponential in epsilon decays, because you have these Fourier modes and you're taking out a sort of fixed size away from there.
Okay.
So it's very circle specific.
Okay.
Also, I think since Gary, you mentioned it, the taking just like a regular, like this, taking this Gaussian kernel, taking your data points, and then just applying synchron onto that matrix. You could show, I think, relatively easily that the uniqueness of the synchron, or I guess you could say Kandorowicz potentials, necessarily gives you that those would be the same matrix in the end. You would get essentially the same.
Synchron is a unique representation if your matrix is irreducible.
Yes. So yeah, I mean, under a reasonable assumption that you don't have like two completely separate markup chains that you're working with, then you would get you could get uniqueness that would show that they're the same. And
so you're saying you get like the two procedures would produce two unique but different things.
no, they should be unique and the same. So I'm saying
Oh, okay.
the uniqueness would give you that they're the same.
Okay, but they're kind of optimizing slightly different things. Because with one you solve this entropy thing first. And
No, but I think it's actually rather that it's two sort of ansatz ways to explain the same
that's very nice.
behavior.
You know, like, yeah, got you in this paper, I don't know. But is
No,
is
I
there
just
a theorem
I was just thinking about it like
that says that
while
that's a nice result.
I was just thinking about it while the talk was going. I think it should be relatively.
All right, maybe I stop the discussion here. We thank Oliver again, and